Hello everyone, this is Vikram and welcome to my channel. This is part 2 of our common AI ML terminology series that we started. In the earlier session, we already covered some of the terms. In this video, we are going to cover 8 major topics. We'll start with what is inference, then move into tokens and embeddings, which are really the building blocks of how language models process texts. From there, we'll look at transformers and self-attention, the architecture that powers every major LLM today. Then we'll get into hyperparameters like temperature, top P and top K, followed by overfitting versus underfitting. We'll cover guardrails, which are critical for safe AI deployment. And finally, we'll talk about sentiment analysis and what is coherence. So let's understand what is inference. Inference is essentially AI in action. It is when a trained model is employed to solve real problems or answer questions on new and unseen inputs. We already seen what is training an AI model. So it also involves updating the weights and all those things. So once the model is trained, it will be employed to solve real world problems like answering questions which can be new and unseen inputs. So when training teaches the model, inference is where it delivers in production, which means inference is actually the AI model which is in production, or the AI model which is answering your questions after it is trained. For example, if you look at this image, during the process of the training, so we have an AI model and then we provide it various inputs, right? So here the inputs are nothing but the fruits. So during the process of training, the model learns the patterns from all these labeled examples, and the AI model is trained. Now after it is trained, so it will be tested on new and unseen data. So this is called inference. So inference is when you give the model the unknown inputs, or the inputs which are not seen during the process of the training. Then what model will do is it will analyze the features, it will compare these features with the learned patterns during the training, and the model will be able to correctly predict the output. So this is called inference in AI. So there are various types of inferences, like batch inference, which usually process large data sets in bulk, ideal for offline jobs or report generation. So there is a real-time inference which handles request on the fly with low latency. For example, in chatbots, if you ask a question, you'll immediately get a response. So this is real-time inference. There is also an edge inference, which runs the model directly on the edge devices like your phones or IoT devices like Raspberry Pi. And edge inferencing will usually have less latency and no networking dependency. So let's talk about what are tokens. So tokens are very important for understanding the embeddings and for understanding how retrieval augmented generation, to be precise, like how LLMs usually work. A token is a small piece of text. It can be a complete word, or it can be part of the word, or a character. So if you just see this example, so I have a sentence or a summary of like what is Kubernetes, and you can see here some of the letters are colored while some parts of the words are differently colored. So these are nothing but the tokens. A token can be a complete word, or it can be a single character, or it can be a part of the word. So AI model works by predicting the next token in sequence, right? We know this. If you have used ChatGPT and if you ask it a question, so it usually responds token by token. It generates the complete response at once, but usually like it will be like token by token, but we will not see that that kind of a flow. So AI model works by predicting the next token based on the patterns learned during the process of the training. So in the process of the training, we train the model with huge amount of text, and this is how it learns those patterns by updating the model weights and all. So it generates the response token by token. So LLMs never see raw text, like this is a raw text, right? It's a complete passage, but it will not see that complete text, but it will only see the tokens. So roughly speaking, 4 characters will be equivalent to 1 token. So which means if you have 100 tokens, it means like it is it is 75 words, right? And if you want to see how these tokens are created from the raw text, you can go to OpenAI tokenizer website and then paste some content and see how the tokens are created. Now, why do tokens really matter? The first thing is like all your LLMs work on tokens. So why do tokens really matter for us? Why should we concern about tokens? Is the first one is token limits or context window size. All LLMs have maximum number of tokens they can handle. So if let's say you're asking a question to an LLM, so it is basically a prompt. So asking a question is a prompt. So LLMs have maximum number of tokens they can handle. So it can be your prompt, it can be your conversation history, and it can be your output response. So basically the combination of all these three is context window size. Once you ask a question to the LLM, it responds, and you ask it a follow-up question, it will again answer, but it will also take your previous questions and its output responses into consideration, right? So this is the context window. So all LLMs will have maximum context window. So beyond that, if you exceed the token limits, so it can cause truncation, which means the output will be truncated, or the LLMs will give you wrong answers, or probably hallucinate, and your output quality will be degraded. For example, if you take the model, various latest models like Claude, Opus 4.6 or 4.7, they have 1 million, context window or the token limit. So which means you can paste an entire content of the book, like 2,500 pages or entire movie screenplay, and still get a relevant response, because 2000 pages means it cannot be more than 1 million tokens, right? So the model will not lose the context, so it will not your output will not be degraded. And the other the reason why tokens really matter is the cost. So all the companies like OpenAI, Anthropic, Google and Microsoft charge per token. So if you use fewer tokens, you'll get lower bills. So you can also consider this example over here. So for example, if I have a book, probably like converted into a text format or a PDF format, and if I calculate the total tokens of that entire book, so let's say it is 250k tokens. And if you are using model GPT 5.4 to process that entire book, this is what you will be charged, because GPT 5.4 has this pricing of $2.5 per 1 million tokens or input tokens it can process, right? So this is how you calculate the total price, right, to process that entire book. And now the strategies for managing tokens is be concise, one clear question per prompt, or you can have a better prompt. Instead of writing a very big prompt, you can have one clear prompt, break long conversations into shorter exchanges, and then summarize earlier parts of the chart instead of carrying them forward. Okay, even if you use tools like Claude Code, they have an option known as compact, where it will compact the entire conversation so that you will not run into token limits. Now, what is a tokenizer? So we have seen what are tokens. So tokens are nothing but a pieces of word, or it can be a character, it can be a word. Now, what is a tokenizer? Tokenizer is a tool that converts the raw text into tokens. Okay, so you can see this image. If I have a raw text, something like hello world, the tokenizer can split them into tokens. So it can be hello as one token and world as one token, right? And then maps each token to a number. Now we will understand why each token needs to be mapped to a number in some time. Okay, so every token gets a token ID. Okay, so token ID is again an integer. So neural networks can only process numbers, not letters or words. That's the reason why we usually convert tokens into token IDs. And these token IDs are just integers. Okay, they have no meaning by themselves. For example, if I have this raw text, write a poem about the ocean, and if I give it to a tokenizer, it will convert into tokens. Like it has broken the entire sentence into individual tokens like this, and tokenizer will assign these numbers. So if you look at these numbers, these are not related. Okay, so individual numbers, okay, are not related to each other. Okay, so even if I convert car and probably like bike to some token IDs, they will not get consecutive token IDs, right? The token IDs can be different. That's the reason why token IDs doesn't mean anything, right? And the token to token ID mapping is fixed by model vocabulary, so you don't get to decide. So this will be fixed by the whatever tokenizer you're using, right? For example, common tokenizers, these are again model specific. OpenAI models uses tick token tokenizer. Again, these are all inbuilt into the model or shipped with the model. Google and Meta models use sentence-based tokenizer. Bird family uses word-based, and each model requires its own tokenizer, and they must be used together. Okay, so after the training, if you try to change the tokenizer, okay, it will not work, because every tokenizer will assign different numbers to different words. For example, right here it is 2456, but some other tokenizer might assign different value to it. And also tokenizers can also split the sentences separately. For example, if you see this BPE, it is dividing the breaking the raw text into tokens very differently when compared to the other tokenizers. So tokenizers cannot be exchanged once the model is trained. And tokenizer components include vocabulary size. Okay, as we already discussed, the word right can have a different token ID, right? So what is vocabulary size is the total number of unique tokens in the tokenizer vocabulary. If you take the like the case of this one, so it is having 50,000 unique tokens, which means it has 50,000 token IDs to 50,000 unique words. Okay, it can be words, characters, or part of the words, or special characters, right? For example, each of these words have different token IDs. That is the vocabulary size. And each tokenizer have different set of splitting rules. Okay, if one tokenizer divides this whole sentence as a single one, the other can divide into unbelievable, right? So again, this is based on the tokenizer, and the value that they assign to each token can also be different, right? That's the reason why once the model is trained, you cannot change the tokenizer in between the model training or after the model training. Okay, so during the process of the training, okay, tokenizer is fixed, as we already discussed. It cannot be changed. The reason why it cannot be changed is, as I already told, every token will have a unique token ID, and this is dependent on what tokenizer you use. So changing the tokenizer during the training or after the training, it will change the meaning of each token, which means the mapping between the token and token ID will be completely broken or completely different. That's the reason the tokenizer files are packed with the model weights, but they are loaded as separate components during the runtime. For example, when you download a model like Llama or BERT or some other models, you will get a lot of files, right? For example, model weights. Okay, so these can range from few GBs to several GBs. Okay, so these contain learned neural network parameters needed for inferencing. Okay, and then embedding metrics, we'll see what is an embedding metrics. So when you download the model, you will also get this embedding metrics. Okay, for example, embedding metrics, I'll just talk about that here. So every unique token ID, for example, this is corresponding to a car. So car is a token, this is token ID. So every token ID will have a learned vector. Okay, so the mapping between these two, this is like token to token ID, but the mapping between the token ID to the vector is so it will have a lot of mappings, right? So it forms a vector known as an embedding vector. And then the tokenizer, so which is basically the mapping between the tokens and the token ID. So if you download a model, all these will be downloaded. And coming to embedding, so now we have seen how the raw text is converted into tokens and how tokenizer will assign unique token IDs. Let's understand what are embeddings, okay, and why these embeddings are really required when you have the token IDs. Embeddings are dense numerical vector representation of tokens that capture semantic meaning. So the word semantic meaning is really important here. We'll understand why it is called semantic meaning and why and how embeddings will capture that meaning in some time. So words with similar meaning have vectors close to each other. That is called semantic, right? For example, let's say car is having this vector. So vector, if you're from mathematics, vector is nothing but it's a point in a space that has both direction and magnitude. For example, if I take a two-dimensional x and y, so if I place one dot here, let's say it is 2, 2, so basically it is having a direction and it is having a magnitude, okay. So if it is a 3-dimension, so you will plot that particular point using x, y and z, right? So it is a point in space that has direction and it has a magnitude. Magnitude means it is the distance from the horizon, okay. So when we plot the vector of a car, so it can, let's say it is here, I'm showing in 2-dimension, but it can be n dimension, okay. Again, this dimensionality depends on what model we are using, okay. For example, if you plot the embedding of the car, so it is here. Now if you look at the embedding of the Honda, so again this is just an example, it may not be true or it may not be an exact vector, okay. So Honda, it is plotted here, and if you plot Apple, it is here. Now if you see car and Honda, we know that they are related to each other, okay. And how these are related to each other, how the model knows these are related to each other, we will see in some time, okay. But now once you plot the vectors of both car and Honda, you can see they are very close to each other. But if you plot Apple, it is very far from each other. So this is semantic. So vector captures vectors for similar words are very close to each other. Okay, so here car and Honda are related to each other. That's why they are very close to each other. But Apple, being it is a fruit, it has no unique relationship between car and Honda. That's why it is very far from each other. Okay, so these are the vectors, right? So how these vectors are created, we'll understand in some time. Okay, so why token IDs are not enough? Okay, so why these are not enough is there is no real relationship between the token and the token ID. So cat is 1024, dog is 5872. Even though we know that cat and dog are related to animal, their token IDs are nowhere close to each other. Okay, that's the reason why the token IDs or tokens doesn't really capture the meaning between those tokens, okay. But if you look at the embeddings, so now how embeddings will be created, we'll see. Okay, if you look at the embeddings of these words like cat, dog, king, table and apple, and if you try to plot them in the vector space, you can see cat and dog are close to each other, king and queen are very close to each other, apple is far apart from these two, okay. Because cat and dog are related to each other, their vectors are very close to each other. That's the reason we go for embeddings. Now what is the reason for going for embeddings? We'll also understand this in this session, and also when we talk about retrieval augmented generation, also we'll talk about embeddings and how these are used in retrieval augmented generation, okay. Now we know that similar words get vectors or have vectors very close to each other. So this will be used for understanding the similarity, okay. So if you see the vectors of cat and dog, so now we'll understand the the relationship between cat and dog, and it will also help us capture the relationships between these words, right? That's the reason, like, we go for embeddings. Embeddings capture meaning, as we already discussed, but how these embeddings are actually created. So are these created by tokenizer or these created by the model? We'll see. Okay, so one example before going to that explanation is, okay, so when a model says I drive a car, okay, and when a model says he bought a vehicle, and if these two sentences occur in a single document, okay, Now the model knows as these two are very close to each other, very related to each other. That is how it will create or update these embedding. So what model during the training does is it will go through training process using huge amount of data, right? And it will see the car and it will see the vehicle text in thousands and lakhs of pages, okay? And this is how it will try to learn the vectors or update the vectors so that car and vehicles are close to each other. It's not something model has decided, it is something that model has learned during the process of the training, okay? So if the model never sees this one, okay, then car may not be very close to vehicle, okay? It's the reason why they are very close, like mother, father, sister, they are very close in the vector space, is because the model has seen lot of sentences where mother, father and sister are referenced in a single document, okay, or thousands of document, that two together, right? Now let's understand what is embedding matrix, okay? So model stores embeddings in a matrix, okay? Now let's forget about how model creates these embeddings, but so once it is created, right, model has to store it somewhere, right? So model stores the mapping. Again, this embedding matrix comes with the model, okay? So once it is created, it will be shipped with the model, okay? So it will store the token IDs, okay, because we already know model only works on token IDs, and for each token the corresponding vector, right? So this is model vocabulary. We already discussed 50,000 is a model vocabulary, and 768 is a dimension of the embeddings, okay? So which means it will have 768. You can say these are like 768 features that are captured, okay? So you can see the dimensions of the entire model, right? So this is a lookup table, okay? For example, let's say the word probably beauty, okay? So this is probably one of the word in the model vocabulary, and it will also have its own vector in the embedding vector, okay? Right. So now how the model creates these vectors is, initially all these vectors start as random vectors, so they will not have the exact the numbers as you're seeing, okay? So they will start as random, and then during the process of the training, okay, so the model will keep on changing these vectors, okay? So through a process known as back propagation. So basically it sees a lot of sentences, right? Okay, and then it will update these embeddings, and once the model is trained, right, so you will see that embeddings, words with similar meanings have embeddings very close to each other, like king and queen have embeddings which are very close to each other, okay? And yeah, so always remember these embeddings are learned during the process of the training, and we will not change these vectors once the model is trained, okay? Because model has seen thousands of sentences, like millions of tokens, and then it understood the relationship between these words, and it has formed the vectors in such a way that similar words will have similar vectors, so they can be close to each other in the vector space, okay? So this is how embeddings evolve. So they start as random, and then the model sees patterns in the data, right? So you can see car, money, run, so there are a lot of words, and then during the process of the training, if the model sees similar words across thousands of pages of the training data, then it will try to adjust them or plot them closer to each other, or adjust the embeddings in such a way that car and vehicles are close to each other, bank and money, loan are close to each other, happiness and joy are close to each other, right? And at the end of the training, you can see that it has captured the meanings, right? That's why it has formed all these clusters, okay? So from word to meaning, what model really sees is, so when you have a sentence, it is broken into tokens. The token will have a token ID, it will be having an embedding, okay? And then embeddings means, for example, this is a bank. So bank is token ID is 5821 and this is its vector, and then if you plot it, it is somewhere here. Okay, now you can see in the vector space money, finance and loan, all these are other vectors, and they're very close to bank because all have similar meanings, right? This is how the model will try to predict the next word, correct? And it will only take the words which are close to each other. Okay, so now we understood embeddings will capture the meaning of those words, right? Let's understand what are transformers and self-attention. Okay, a transformer is a deep learning architecture that processes entire sequence of text, okay, at once rather than word by word. Okay, for example, if I say let's say I love Paris, okay, or the better example is, let's say I went to the bank to deposit money. Okay, so instead of saying one word after the other word, okay, what transformer architecture will do is it will see the entire word at once. Okay, and this is how every major LLM work today. Okay, so transformers use something known as self-attention. Okay, self-attention is algorithm. Okay, so this makes transformers very powerful. Okay, so this self-attention allows the model to look at every word in the sentence simultaneously. Okay, and decide which words are relevant to each other. Okay, the example is I went to the bank to deposit money. Now let's forget about the other parts of the sentence. Let's look at only the bank. Okay, so what can the bank word really mean? So it can be a river bank. Okay, it can be the money bank, right? It can be financial bank, right? Or bank word can be anything else. Okay, so if you take them in the vector space, bank doesn't mean that it is something related to financial bank, but bank can also mean something related to the river. So now how will a model generate a response if it doesn't know we are talking about the financial bank or the river bank or something else? Okay, this is where self-attention comes into the picture. So instead of reading one word after the other and getting confused, self-attention will see how each word is related to the other words. So in this case, bank is more related to the deposit or the money. Okay, so this is how the model knows that this is not a river bank, so this is a financial bank, and this is how it will generate the response which is related to the financial banking. Okay, while embeddings capture the meaning, okay, of each word in the sentence. Okay, it doesn't know how one word is related to the other word. Okay, so we know that king and queen are very close to each other due to embeddings, but how king is related to the queen, how a car is related to an automobile, okay, so we will not know directly through embeddings. Okay, of course through embeddings we know the closest words in the vector space, but we'll never know what is the relationship between words in the input text. The self-attention is where we get contextual meaning. Okay, so what is a context is like when you ask a question to the AI model, that becomes your context, right? It's like what you're talking. Okay, contextual meaning is only captured through self-attention. So self-attention checks how each word is important to the other word. So here bank is very important for the money, for the deposit. So these words are very related to each other. So this is how it understands the context. Okay, so instead of bank paying attention to I went, so it pays attention to bank, deposit and money, and this is how it will understand the bank and how it is related to the entire sentence, okay, or the entire input. So without which AI models cannot give you better responses or the accurate predictions. Okay, now let's understand the end-to-end process before going into in-depth. So when you give an input text to the model, it will convert into tokens, and the tokenizer will assign unique token IDs, and then we have embeddings, okay, or the embedding metrics here, where every token will have a unique vector in the embedding matrix. Now again, as we already discussed, directly through embeddings we'll not understand the context of the input. Okay, So these embeddings, all these embeddings for all these words will be sent to the transformer, which uses self-attention to give contextual representation of all those vectors, and these vectors are used to generate the response or predict the next token. Okay. Yeah, as we already discussed. Okay, so why token IDs over embeddings is this one. Okay, so embeddings capture the meaning and self attention will give you the contextual meaning of all those embeddings. Okay, yeah, so now let's understand again one final time how LLMs process your question. Okay, so I asked it what is the capital of France. Okay, so the tokenizer will convert into tokens and assign unique token IDs. Okay, and these token IDs are sent to the model. Okay, so the model will have the embedding matrix. Okay, for each of the token there is an vector associated with it. Okay, and all these vectors are together sent to the the AI model, which is nothing but the neural network model. Okay, so it will understand through the process of self attention, it understands the relation between all these words. So here capital and France. Okay, so it will understand the relationship. Okay, and then it generates the response. So it will not generate the text response directly, it is going to give out the token IDs, okay, of the response. Okay, and these token IDs are sent back to the tokenizer. Again it will detokenize. Okay, for example, the output of the transformer is 76543456 and 1111. This is nothing but the the IDs for the text. Paris is France's capital. Okay, so the tokenization happens here and the response is shown to the user. So this is how the LLMs process your the entire input. Okay, now let's understand the term hyperparameters. Okay, hyperparameters are the settings that control the model behavior. Okay, some hyperparameters are used before the training, some are used during the inference, that is once the model is trained. So unlike parameters that a model learns from the data, okay, like the weights or the embeddings, these are not learned by the model, these are externally configured to affect how a model performs. Okay, so these parameters include influence the randomness, the diversity of the output, or the length of the output. Okay, hyperparameter tuning means testing these different combinations to find which combination will lead to better performance. Okay, that is called tuning of these hyperparameters. There are two types of hyperparameters. One is training hyperparameter, the other one is inference hyperparameter. Now we'll understand so training hyperparameters we don't have to understand in depth as of now. Okay, so we'll mostly concentrate on the inference parameter. Okay, now let's try to understand what each of these words mean. Okay, without an example. The first one is a learning rate. Learning rate controls the step size for updating the model. Like we know that the model weights are updated during process of the training, so it controls the size or the step size for updating the model. Batch size is the number of samples processed before updating the model. Let's say I have 1000 pages document that I'm using to train the model. So batch size indicates the number of samples, like, or the number of documents that are used that are given to the model before updating the weights. Epochs are the number of complete passes through the training dataset. So if a training dataset has 10,000 pages, epoch indicates like how many times the model has seen that complete dataset. Okay, and inference parameter, we have like temperature, top P, top K, and maximum tokens. Okay, so let's understand what is temperature. Temperature controls the randomness or creativity of the model output. Okay, so how the model can be how creative the model can be. Okay, so before understanding the other ranges and the values, let's see what will happen if we have low temperature values, medium, or high. Okay, so the question that we have is what is the capital of France. Okay, so if I have low temperature, you can see the response is the capital of France is Paris. It is straightforward, it is more deterministic, it is expected. Okay, If the temperature is medium, let's say temperature is in between 0.5 to 0.7, let's say, now you can see the model, model's creativity has increased a bit. Instead of directly responding the capital of France is Paris, it is saying Paris is the capital of France, known for the Eiffel Tower, right? So it has more balanced output. Okay, now what will happen if I increase the temperature value? Okay, uh, you know probably like 0.8 to 1, or even more than 1. Okay, it becomes more creative. So Paris, the city of lights, is France's vibrant heart. Okay, you can see it has generated a creative response. Okay, the range of temperature is 0 to 1. Okay, sometimes more than 1, like 2, depending on the model. Lower values always gives you more deterministic, focused, or repetitive response. Okay, higher values will give you more diverse, creative, possibly more errors, and less coherent. So we'll also understand what is coherent. So you can see lower values will give you more balanced and focused output of the model. Okay, if you set k to something 1 or more than 1, it will give you more creative, but it can also introduce some errors. Okay, for example, let's say the word your order is delayed, please wait. Okay, so this is the response, probably for lower values of k. But if you go for higher values of k, looks like your order hit a delay, let me help you track it. So you can see it has become more creative, but sometimes it can also give you errors as well. Okay, now what is top p? So top p is Nucleus sampling. Okay, so limits the sampling pool to the top tokens that make up the cumulative probability mass. So this can be quite confusing. Okay, let's see the range of this. This is 0 to 1. Okay, what is this is, you can take it as probability. Okay, so we all know that the model responds by token. Okay, and we also know that embeddings for the similar words will be very close to each other. Okay, when generating the output, the model will have several choices, right? For example, the next token choice is, you can see these are all the token choices that model can use to generate the output response, right, for forming the sentences. Now if you set the top p as 0.5, so what it will do is it will calculate the cumulative probability. Okay, so the probability of every word is different. So if you add them, okay, so it is, let's say if I have p as 0.6, you can see here p of 0.6, it is cumulative is ending here, because cumulative is 0.65 here, rp is 0.6. so only the word will be used for generating the next token. Okay, for example, if you have top p set to 0.9, so it will consider all these tokens for generating the next token. Okay, it can use any of these words, okay, while ignoring the rest. Okay, so lower values will have less random words. Okay, but higher values will have, because we have more choice of the next token, so the model can become more creative. Okay, this is a top p, which is the probability. Top k is the top k tokens that model can use to predict the next token. For example, the range is, it can be go from 0 to 100, or 0 to 100, let's say. Now if I set top k as 40, okay, so what it will do is it will take topmost 40 tokens and then use it to generate the next token in the response. Okay, so if I set low k, less randomness and high probability, so if I just select k as 5, so the model can use only these words to predict the next token. Okay, higher k means you'll have more choices, so the the model can become more creative. Okay, for example, so these are the settings that control model output, and we can use these combination. So if you want the output of the response to be safe and deterministic, okay, so we can use lower temperature, because higher temperature will make the model more creative, okay. And then you can use fewer tokens, I mean like top k tokens, and the probability can be 0.8 to 0.9, okay. So which will be used for code generation or strict instructions, okay. So if you want more balanced output, you can use medium settings of temperature and top k and top p, these settings, okay. So these will be used for in case of summarizing something, okay. You want the model to be very balanced, not very creative or not very deterministic, okay. So if you want the model to be very creative, you can use high temperature, high top p and top k settings, okay. So this is extremely creative, but this can also lead to the model predicting outputs which are not completely true, okay. Yes, so you can use this also as an example, okay. You can see my prompt is explain the importance of drinking water. Now let's see how it impacts, how the response impacts, right, is impacted using the temperature, okay. Now let's say the model you know have all these for predicting the next tokens, okay, and these are all the probabilities, okay. So when you use lower temperature, okay, so what will be the response is drinking water is essential for our bodies, okay, it is safe, predictable. But if you use medium temperature settings, we know that model will start to have more balanced, okay. So you can see here it is saying drinking water helps keep our body functions running smoothly. So it is very different from the lower temperature based response. But if you have high temperature, you can see the model is becoming very creative, okay. So drinking water is absolutely crucial, it keeps everything working and you feeling great, okay. This is very creative output, okay. And top p, so this is Nucleus sampling. If I use top p as 0.5, okay, so what it will do is it will end the responses uh, you know till 0.5 cumulative probability. So 0.5 is still here, so it only uses this word, that's the reason why it is using keeps, okay. If it is 0.8, so the model can consider all the words till cumulative probability of 0.8. So you can use any of these like helps, is, keeps and all, okay. Top p means it can top p of 0.95, it is here. So you can see it is using ensures, which is here, okay. So this is how top p, top k and temperature. So you can pause the video and understand how top k change the model output behavior. Let's understand what is overfitting versus underfitting. Overfitting and underfitting are core machine learning problems representing poor model generalization, okay. So you're trying to create a model, okay, and this model is a you want to use it as a general model for all the queries, okay. But there are things that impact the model generalization, which are overfitting and underfitting. So overfitting happens, okay, when the model learns too much from the training data, okay. So you have billions of tokens as the training data that you use to train the model, right? But what will happen in this case is, since the model is learning a lot from the large data sets, it can also learn from the noises and outliers, okay. So which means it, instead of learning the correct things, it may also learn the noises or unknown data or outliers, right? So it performs very well on training data. The reason why it performs very well on the training data, because the model is already trained on huge amount of data, okay. So if you ask it any questions which is already there in the training data, it will respond properly. But if you test it on unknown or new inputs, it may not work properly, because the model has learned too much. It is just like memorizing the answers instead of learning the concept, right? So to fix overfitting, okay, what we can do is we can add regularization, okay. Regularization means not updating the weights abruptly. We can use dropout. So dropout means like we can turn off certain neurons during the training to prevent the model from learning too much from the patterns. Early stopping stops training when performance on validation data stops improving. Okay, let's say you stop training the model when it is not performing well on the validation data set. Okay, or else what you can do is you can use simpler models, okay, which will have reduced parameters or features. Okay, but underfitting is when the model doesn't learn much from the training data, while overfitting is like you're learning too much. Okay, but underfitting is when the model hasn't learned too much from the training data. Okay, it can be due to anything, like it can happen when we don't have much training data as well. Okay, so the model is too simple, it couldn't capture all the features from the training data. So that's the reason why it performs poorly on both training and new data. Okay, because the model is too simple. Now in order to fix the underfitting, you can use more complex model or have data set with more features. You can do training longer, okay, reduce the regularization, okay, or get better quality data. I forgot to talk about this one. So here the training data shows the student exam scores based on the number of hours they study. Okay, so if someone studies for 1 hour, the score is 50. Okay, and then if someone studies for 10 hours, it is 98. But here there is an outlier. If you see, if someone is studying at 8 hours, they'll get 100 score. Okay, this is the training data. Okay, so the model, it has learned all the features, but it has also learned the outliers or including noise. Okay, now if you try to test the model in the real time, okay, you can see here, if someone learns for 1 hour, they'll get 51 score. Okay, and then if as the number of hours increase, okay, usually the score should increase. But if you see suddenly someone is learning for 11 hours, it is saying they get only 70 score, which is not right, because the model has learned a lot, it has also captured the outliers and noise. Okay, but here it's a different thing, right? Here same example, okay, but the model is simple, it did not capture all the relevant features. Okay, so the training data is same, but if you look at the model, okay, so if you see here, it has not learned anything properly because of the model is too simple. Okay, you can see here it has not captured all the meanings. So for someone who learned who studied for 10 hours, the score should be 98, but it is not giving that 98. Okay, because the model is not trained well because of less number of features or model being too simple. Okay, now coming to guardrails. So guardrails are safety mechanisms built into AI systems to prevent biased, inaccurate or misaligned outputs. What is the meaning of this is, if guardrails are not there, okay, if I ask it a question on how to create an atomic bomb, okay, or something which which shouldn't be answered, okay, right, this is where guardrails comes into the picture. So guardrails will prevent AI systems you know from answering biased or inaccurate or misaligned outputs. Okay, so the guardrails can prevent harmful or unsafe content. Okay, for example, violence or illegal action, so it will not generate responses that can be harmful or unsafe. Or they can also block sensitive data exposure. Okay, for example, let's say during the process of the training, it has also learned some passwords or some secrets or credentials. Okay, but using guardrails we can prevent the model from exposing the data, exposing personal identifiable information like someone's email addresses, someone's social security numbers, or someone's credit card numbers. So the model can actually block the responses, or mask these things in the responses, or doesn't show these information in the responses. Reduce hallucination. So hallucination is, we already spoke about this in the previous terms. Hallucination is something the model will give you inaccurate answers which seem to be very accurate and very genuine, but these are the responses that model created on its own, and it is not basically learned during the process of the training. Okay, so you can also reduce hallucinations. Okay, and then keep responses within scope, like making the model responses scope to internal documentation or domain specific responses instead of the model answering the questions. Let's say, can you explain the features of, or you can say, what is the sales data for 2025? Okay, let's say I have a model which is hosted internally in the organization, and I want the model to only generate responses only from the company's data, not from a general perspective, right? So in this case, guardrails can help prevent the model from giving responses out of scope of the domain, right? And ensure compliance and policy adherence. Okay, so we can use guardrails so that the responses can follow compliance and other legal requirements. Okay, so this is how, like, when a user asks input to an LLM or an AI model, say AI model generates responses only on the trained data. Okay, but we can also have the guardrails layer, okay, something like safety checks to detect the the content, safety, bias detection, fact checking, policy, and then it will filter that response, okay, or block that response, right? So, and the final one will be safe and aligned AI output. Okay, so guardrails can be safety guardrails or bias guardrails. We'll understand what is bias in some time. Accuracy guardrails, policy guardrails, or privacy guardrails. Okay, and guardrails can be defined into LLM providers. Okay, so OpenAI, Anthropic, Gemini has their own internal guardrails. Okay, so their output is unbiased, safe, right? Following certain policies. Okay, so you can also have prompt level guardrails. Okay, so when giving prompts to the AI model, you can structure the prompt in such a way that you can ask the model to avoid biased or unsafe responses. You can see here, you're a helpful assistant, avoid biased, harmful, or unsafe responses, like this in the prompt itself. Or you can also have application level guardrails built in even before your query goes to the LLM. You can also have an input guardrail to block unsafe or biased or prompt injections directly before the LLM. And you also have framework or library level guardrails. For example, LangChain, Llama Index comes with their own set of guardrails as well. Okay, now we understood guardrails. So guardrails prevent the biased outputs, as we already discussed. Okay, so bias is when AI model produces unfair or skewed outputs towards certain groups or reasons or people, right? Fairness is when AI model treats everyone equally. Okay, so the best example is bias is, okay, so if you see here, when there is a word leader, it is associating with he. Okay, so this is a bias, right? She can be a strong leader as well. And when it sees emotional, so instead of saying he or she is emotional, so it is relating that emotional word with she. Okay, so which is completely bias. Okay, and some bias can also mean, like, if the job is an engineer, it is associating with he or man, and if it is nurse, it is associating with gender woman. Again, this is a bias, right? So bias can happen in many ways, right? Because the training data doesn't have information of unbiased things. Okay, so bias can come from the training data as well, right? And what is fairness is when AI model will treat everyone equally. Okay, so it is treating both man and woman as equal. Okay, not based on the gender. Okay, even for the skills, it is not associating a specific skill with a gender, right? This is bias. How to address bias and promote fairness is, we can have balanced and diverse data set that capture both man, woman related information, okay, or the data. Evaluate model across different groups, add guardrails to filter or correct output. Okay, so you can do all these things, right? So if you have very good data set that captures all the features, and it will not probably lead to bias. Okay. Sentiment analysis is the NLP task, okay, to identify and classify the emotional tone expressed in text. Okay, so that can be positive, negative, or neutral, or it can be happy, sad. Okay, so it is one of the most widely used AI applications, okay, like customer feedback analysis or brand reputation tracking, market sentiment, support ticket optimization. So even if you see once the support ticket is closed, you will get either thumbs up or thumbs down, right? So this is sentiment analysis, which actually evaluates the the sentiment in the response. Okay, so you take the input, and NLP will process it using NLP techniques, and it will detect the sentiment. Then the text is either labeled as, the output is labeled as positive, neutral, or negative. For example, if someone says I love this product, the NLP can classify it as positive. The product is okay, not great, it can classify as neutral. This is the worst experience ever, this can be classified as negative. Okay, so coherence, we already talked about coherence in the previous slide, coherent output. So coherence in AI refers to the ability of the model to generate response which is logical, consistent, and relevant to the input. Okay, so I asked it a question, what is the capital of France, and if the output says something else different, that is not a coherent response. So the output should be logically aligned and contextually relevant to the input or the interactions that we do with the AI model. Okay, so that factors that can affect this coherence is the temperature settings, or the context window size. If we run out of tokens, the LLM might not be able to provide the coherent responses, right? And even the temperature settings, if you set them to high, the model becomes more creative. Sometimes it will lose the it will give you non-coherent responses as well. Okay, the coherent responses is when if you see the model is responding like this: electric cars are popular, the moon is made of cheese. So it is switching or jumping the words randomly, no logical flow, and it is very hard to understand. Coherent response is when the responses are connected with the inputs, logically aligned with the questions that we are asking, right? So electric cars are becoming popular because they reduce pollution and save fuel costs. You can see here the entire sentence is coherent. Okay, and we have many techniques to evaluate coherence, because once the model is trained, okay, we have to evaluate it whether it is generating the responses which align with the input or match the conversations that we are having with the AI model, right? So one evaluation is human evaluation. Okay, so which is kind of a gold standard, but it is very slower and expensive, because humans will be involved to see whether the responses are coherent, fluent, consistent or not. And LLM as judge will have another LLM evaluating this response. Okay, so it is very fastest way for measuring the coherence, by employing another LLM to check the output, right? And semantic similarity, which captures the meaning in the response. Okay, this is another way to see whether it is coherent or not. Okay, so if this is if this is not a coherent response, what will happen is the responses will have words which are very far from each other, so they are not semantic. They will not have any semantic meaning to them. Okay, perplexity, okay, this is other evaluation metric. Okay, so usually this will check the language quality. Okay, so it will check whether the language is fluent or grammatically correct. And then blue or rogue, so it will evaluate the response with a reference response. Okay, then it will see whether the generated response and overlap and referenced response have any overlapping of words or not. So higher overlapping means the model is coherent, right? So these are the various evaluations. We don't have to know anything as of now. Okay, Yeah, that's it for this video. We have learned a lot in this video. In the coming video, we'll learn about hybrid search, semantic search, retrieval augmented generation, vector databases, and a lot more topics around retrieval augmented generation. Thank you, and I'll see you in the next one.